All right. All right, this is part two of the hypothesis slash significance test, whichever one you want to call it. So we're basically testing um, if what we believe is true from the null, basically. So the null hypothesis, typically is H0 or Hn. The alternate hypothesis usually H1 or HA. We're going to stick to 0 and A because I believe that's what this textbook uses. Um, So the default belief or the null belief, you always use equals. The alternative is either less than, greater than, or not equal to, essentially. Okay. So even though the null hypothesis might state in the problem that's greater than or equal to or less than or equal to, you still do equal to. Okay. Um, and the null hypothesis is always equal, and the null hypothesis is never equal. Okay, that's basically what you think of it. So even though the statement that's being made by the problem might be saying this, you still write it as equal, basically. Okay, so these are some common phrases that are used. You might see. So essentially, there's only really three tests that you do. So we'll do the same three tests for difference of two proportions, means, all the other different type of hypothesis testing we'll be doing over the next month. Um, so if it's a right-tailed test, then you're testing to see if you're in this region over here, right? That's a right-tailed. If you're a left-tailed test, you're seeing if you're in this region, right? That's this one right here. Otherwise, if it's a two-tailed test, it could be either one. So either you're in this region, or you're in one of these shaded critical regions, basically. If you're in a shaded critical region, which could be either one of these, that means you found enough evidence, basically, which is how a hypothesis test works. Because if you're in here, you did not find enough evidence because this is your z equals 0 value, right? So that's basically default belief average, right? If you've made it out to here or here, you found enough evidence. It's very significant, essentially. Okay, so there's basically four steps of a hypothesis test or statistical significance test. The book does five because it takes the p-value as its own step. I'm not going to do the p-value as its own step. I think that's kind of silly. We're just going to put that into the other steps, basically, as far as so when you calculate all the other things, just calculate p at the same time. We'll call it 4. If you want to do it as 5 like the book, that's perfectly fine. Okay, so the test statistic for proportion is z. It could be t also. We'll do t when we do means. But for the most part, the ones that are not z are specialty, not usual cases, so we're just going to ignore those and just basically use z. And typical z value, it's the sample minus the proportion divided by the standard deviation, right? Okay, so the alpha level, the significance level is still alpha, okay, which does relate to the confidence interval, but we'll talk about that next week. So basically the idea is if the p-value, the probability value, is less than alpha, you need to reject the null hypothesis, okay? Which means you've made it into the small little shaded area. If the p-value is greater than alpha, you do not reject the null hypothesis. Basically, the default belief is probably true, essentially, which means you're basically in the middle area, right? So if the p is very small, that means you've made it out to here or you've made it out to here, essentially, right? If the p is very large, you're in this area. Okay, we'll go through that pictorially later on. Okay, so basically the samples have to be random and independent. Okay, and it had to become some kind of binomial experiment. And the sample sizes must be greater than or equal to 10 for success and failure, essentially. If that's not true, then you can't actually do the test. Okay. So basically think of it this way. If the p is low, the null must go, which means you've basically proven what you're trying to figure out, essentially. So let's try one here that I've made up. So a statistician reads that at least 77% of the population opposes replacing a $1 bill with a $1 coin, right? So that's a default belief that the government's giving, I guess. To see if this claim is valid, the statistician selects a random sample of 80 people and found that 55 were opposed to replacing the $1 coin. 70% of the population are opposed to the change. Okay, so let's try it like this. So step 1, okay. So why is it double spacing? Hold on, I don't know why it's double spacing. Let's stop that from doing that. Okay, so the parameter of interest P is the proportion of people who oppose replacing the $1 bill with a coin. Okay, I don't know why that's bold. Let's unbold that. I don't know why that's bold. Okay. This will be a 1. Why is this I don't know why this keeps doing this. Let's get rid of a 1 sample z-test for the proportion of people opposed to replacing the $1 bill with a coin. Okay, so that's basically the parameter of interest, right? And then this is the test we're actually doing, which is the proper test for a 1 sample proportion. Okay, so our hypotheses, H sub 0 for our null is what we're going to be using, and H sub A is what we'll use for alternative, essentially. Okay, so P is equal to 0.77. Okay, let's shrink that down a little bit and think about why. The statistician reads it at least 77%, which means greater than or equal to, essentially, right? But you don't include the greater than in the null hypothesis case. It's always equal to. So the opposite alternative would be less than 0.77. Okay? So there's our hypotheses. Either one or the other is true. Both cannot be true. Okay? All right, step 2. All right. All right. N times P equals, so we have 80 samples at 0.77, right? Because it said the test claim is at least 77. That's what we're doing, right? So that would be 61.6, and then if I copy this, copy paste, N times Q, success and failure. So the failure would be 23%, so that would be 18.4, right? All right, so that means that we have enough samples. So they have to be 10 or more for each of these for it to be a valid test, essentially. Okay, and we need our sample proportion. Our sample proportion is going to be 0.77, right? It should match the population. And then the sample deviation, standard error, for the sample, it is the square root of 0.77 times 0.23 over 80. We don't need the exact value there. We'll just keep it as is. We'll put all that into the spreadsheet afterwards, right? Okay. There's your standard deviation formula, right? Because remember, you have to divide by the population size for the central limit theorem, right? From the prior course. Okay. Actually, we should make that bold, though. Bold. Maybe this is why. I think that's why I screwed up the last one. Okay. So there is enough samples. The samples are most likely random and independent. There's no way to otherwise. There's no reason to believe otherwise. You're taking from the whole population. So typically, even though you're taking one from the population, not replacing it, which technically is dependent, since it's a population model, it's less than 10% of the population. Therefore, it's using the population rule of thumb, where it doesn't matter because the population's so large. Okay, step 3. Step thrice. All right. Math type p hat. So the actual sample that we went out and got gave us 55 out of 80. So 55 out of 80 was our sample, right? That's obviously not everybody in the entire United States. So that's 0. You actually just keep it as is. Okay, so my z value is observed, right? Minus expected, so 0.77, right? So it's usually sample minus population, observed minus expected, however you want it, over the standard deviation, which in this case, I guess I'll type it again, why not? 0.77, 0.23, and 80. Okay. So we're going to use those to figure out the area. Okay, so the area equals the normal CDF, normal dot distribution. Okay, we're going to pause there. All right, so it's going to do a little picture here, basically. So if I draw a little picture, actually, you know, let's put this in the spreadsheet first, because I'm going to need my my P and Z value, actually. Let's do that. So let's go to my spreadsheet. And I'm going to rename this Part 1, Part 1. Add another tab, rename this Part 2. Okay, so P hat for us was 55 out of 80, right? So equals 55 out of 80. Okay, then our Z value, right? So we'll do parentheses, so it's this minus the 0.77, right? Divided by the square root of the 0.77. Oh, that's not the right direction. What am I doing? 0.77 times 0.23 divided by the 80. Okay, so I think I got it as my z value. Okay, so negative 1.75 is my z value. Okay, so let's go back to here. We'll just put an approximate for now. We don't need to worry about the rest of the decimals when we draw our picture here. Okay. Actually, I don't know the confidence level. Oh, alpha is 1%. That's what we want. Okay, so alpha is 1%. All right. So I'm going to draw a normal curve. It's the same picture every time, just different shading, you know what I'm saying? So this is a left-tailed test, right? So basically, this area over here is 0.01 because that's alpha. Okay? So the question is, when I do my area, is it in here? Let's just shade this, right? So this is 0.01, right? That's my alpha. Okay? So there's only one of two things that are true. Either my area will be out here or in here essentially, right? So if it's in here, that means it has less area than 0.01. If it's out here, it has more area than 0.01. If you have more area, right, the p-value is greater. So it's either this p or this p. We don't know which one, okay? So if p is bigger than, it's going to be out here because that's how we have more area in the curve, right? Otherwise, it has less area in the curve. There's only two things possible, right? Either going to be less area, or you're going to be more area, right? So if you're more area, then you're in the conventional wisdom, basically. So null hypothesis is probably true. So you don't reject the null hypothesis. Okay. So the thing is, when you do this, the normal distribution function does all the area left to right. Okay? So what we want to do is z, comma 0, comma 1, comma true, which means to add up continuously. You're adding up all the area left to right. Okay, so let's go back to the spreadsheet now. So the area equals the normal dot distribution. See how it pops up there too? The z value, comma 0, comma 1, comma, see how it says cumulative, right? Or not a mass function, but cumulative, which is true. So add up all the probabilities, and we get this basically. So 0.039764. 0.03964, is that what I said? I believe that's what I said. Dot, dot, dot. So that area is also known as the p-value, the probability value. Okay. All right. So step 4, okay, is making our conclusions now. Sometimes they do the p-value step as a separate step. We're not going to do that. So essentially, the p-value is greater than alpha because that was 0.01. Whoops. So we should, whoops, do not reject the null hypothesis. Okay, so let's think about that again here. Let's draw a little picture. All right, that is not the right color I want to use. Let's use black. There we go. All right, here a little picture. Here, so my alpha is 1%. All right. So this is known as the critical region, where that means my sample is significant, basically. So my sample was the 55/80, but I got about 3%, so it means I'm out here, basically. Right? So my p-value was 0.039, right? Which means it has more area than this one than my alpha, right? So that means it's close. It's in this region, which is not very significant, basically. Okay, so therefore, it did not make it to the critical region. If it was in the critical region, that means I can. It's significant enough to reject the null hypothesis. So conventional wisdom basically wins out. Over here would be conventional wisdom does not win out, basically. So you have to reject it and go with the alternative. So there is not enough evidence to reject the null hypothesis, hence H sub 0, right? The sample was not significant, right? So a sentence in context would mean it is most likely true that 77% or more of the population opposes replacing the $1 bill with a coin. So that's the sentence in context, basically. Okay, so we do not reject the null hypothesis. That means the null is probably true. Notice how I'm saying most likely, because again, just like confidence intervals, you're never absolutely sure, right? All we know is it's the most likely outcome based on the evidence that we have. So we have to go with the basic standard belief because we didn't prove otherwise, essentially. Okay, so that's a left-tailed test. You could also have a two-tailed test or a right-tailed test. So for the next problem, I've already done them out. You can reread them for yourself later on. So a quarter of lawyers publicly advertise for new clients, and attorney claims that more than 25% of lawyers advertise in New Hampshire. Okay. Um, so basically, a quarter of lawyers publicly advertise is the default belief, right? So it's a quarter equals, right? But you believe in New Hampshire it's more than that, so it's not normal, basically. So it's still a one-sampled z-test. The proportion of lawyers that's advertising is the population of interest here, correct? So we want a 5% alpha, right? So the area is 5% for alpha this time, correct? So this is alpha, which means it's 95% over here, right? So this is equals 0. Okay, so we do our normal tests and do all our z and all that, but this time you notice I did 1 minus this, right? Because here's the problem. If you do the z value and the distribution function to get the area, right? That z value is from here to here, left to right. Because essentially these are calculus functions and they're doing the area left to right. So in order to get the area over here, I have to do 1 minus that answer. Because if this is, I don't know, like 95%, then the 5% is over here, right? So you have to do 1 minus to get that answer essentially on the other end. So what you'll notice in this case, when I do this, I get 0.01. And the alpha was 0.05. So that means the p-value, that's wrong, p-value is less than alpha, okay? Which means you reject the null hypothesis. Our sample portion is significant and is likely not to occur, which means basically our sample, right? Our sample for this problem is significant. It's not likely to occur, which means it's in the critical region, right? So you notice that when we did this one, it's in the critical region because it is less than the alpha, which makes sense. It's less area, right? It's significant. It made it to the so this is just default null belief. It actually made it out to there. Again, this is not to scale. It's something I drew. Okay. There's enough evidence to support the alternative hypothesis. In context, it's likely true that more than 25% of New Hampshire lawyers advertise. So the default belief for most lawyers is 25%. In New Hampshire, we think it's different, and we think we proved otherwise. Are we absolutely sure? We are not sure. Okay. But we hedged our bets. So that's a right-hand test. So you have to do 1 minus to get the area there, essentially. Okay. What about a two-tailed test? So Center to Disease rule says 70% of young people are obese. Okay. We think that's not true. Okay. And we're going to do an alpha of 5% again here. Okay. So basically, this time I did a not equal to, because we're not saying whether we believe it's more or less than 17%. We just don't believe it's 17%. Okay, so the parameter is the proportion of the kids that are obese in that age group, young people, and it's still a one sample z-test. Okay, so we do our calculations. It's still more than 10. This is our sample here. Okay, this is our sample. This is our z, right? But here's the problem. Okay. Oh, this is normal dot distribution. This is incorrect. This is normal dot distribution, and I have to do 1 minus, and then put parentheses around the whole thing. And let's think about why that is. Okay, so I got a positive z-value of 1.5, right? So if I go up to my picture, I don't see 1.5 up here. I did. Oh, but I got this one right here for a z-value 1.5, didn't I? So there's my z-value there. It was 1.5. And I got this as 0.066 as the area. Huh, that's interesting. So if I go down to here, I actually got 13 as my area. Well, why is that? Because I also multiplied it by 2. Well, why did I multiply it by 2? Well, this is a two-tailed test. It's not less than or greater than. It's not equal to, so it's two-tail. So the p-value is actually double the whole thing, right? So if I divide that by 2, then I'd get 0.066, so 6%, right? Because it's about 13-ish, so 0.66 in either end, which is less than the alpha. So my alpha is 5%. But this is a two-tailed test, which means you have 2.5 on this side, and you have 2.5 on this side, okay? So when I get my p-value divided by 2, right, the question is that greater than or less than? So that's greater than, which means it's not going to be in this area. So why did I have to do 1 minus? Well, I had to do 1 minus because I get a z-value up here, which means I'm doing this end. And the area goes left to right, essentially. Okay, so let's review. So I had to do the 1 minus because I have a z-value on the high end, right? So if I'm on the high end, right, I need this area over here, which means if I calculate it, it's going to give me this area. So if I do 1 minus this area, I'm going to get that area, essentially. And I did that because I have a positive z-value on that end. But I also have to double it because the total area is actually both ends because it's a two-tailed test. So whether you do the half rule or not doesn't matter, because for a 5% test, that is still less than the 13, right? Which at the end of the day means our sample is not significant, right? Which means the sample that we found is not significant. It's a pretty normal sample, which means we're not going to reject the null hypothesis, okay? Because that means if p is greater than, that means we're in this area here, which means we're not in the critical region. That's a critical region, or that's a critical region, right? So we basically assume the null hypothesis is true. Okay, so in context, the CDC findings that are likely true that 17% of young people are obese. Is it more or less? It might be, but we didn't prove that though, because the evidence that we found based on our sample was not good enough. It was a pretty likely sample, essentially. Okay? All right, but there's another, what happened here? A little bit of a problem here. There we go. Okay, let's say the Medical Leave Act, 60% of people found it was easy to use. But we don't believe anymore, years later, that it's still 60%. We think it's now different. So now I'm going to use an alpha of 0.075, so 7.5%, which means 3.75 on either end. Okay, again, area, not to scale. My art skills are terrible, right? Okay, so this is still a one sample z-test. So it used to be 60%. We think it's different than now. So I do my math, and using my sample, I figure out the area. But this time I get a negative z-score, right? Which means I'm on this end, right? Which means I don't need to do 1 minus, because this z is a negative z, right? I don't need to do 1 minus, okay? So this is actually going to be normal dot distribution. And this again, p-value. Sorry, I typed these earlier. I made a few typos. P-value. Okay. So I don't need to do the 1 minus, but I still need to double it because it's a two-tailed test. So I get 0.066. Okay. Well, 6619, whatever it is, you know what I'm saying? Okay. So essentially, if you think about it, that is less than the alpha, so I should reject the null hypothesis, right? So this is smaller than the alpha. Okay? So essentially at the end of the day, right, what I found is smaller than the alpha, which means it's in the critical region essentially. Okay? So as a result, our sample that we found, right, so this is our sample that we found that was given to us when we did the statistics, was significant. It was in the critical region. We assume the null hypothesis is likely false, which means we're going to accept the alternative hypothesis. So in context, it is likely true the percentage of people that find the MLA easy to use has changed. Has it gone up or down? I don't know. We really can't say that. That would need a confidence interval for that, basically. So basically, at the end of the day, you have to pay attention to, is it a one-tailed test or a two-tailed test? If it's a two-tailed test, you have to double the area, and you don't need to do 1 minus if it's a negative z-value. If it's a two-tailed test, you need to double the area. If it's a positive z-value, you still need to do 1 minus. Okay? If it's a right-tailed test, you must do a 1 minus to the area, to the function that you do. If it's a left-tailed test, you don't need to do that, basically. Okay, so that's the basics of hypothesis testing for